There we go. Okay, all right. So here's, we're actually going to do some Math 212 today. So we'll start off by talking about points in Rn. So what is a point in Rn? Well, this is a pretty easy concept. I'm not going to spend a lot of time on this. You already know this one. Points in R2. This is what y'all commonly see as the XY plane. Just FYI, there is no law that says that the variable for that horizontal axis has to be called x. That's not a law. Very often it's called, like x, we call these variables x1 and x2 instead of x and y. If you take an econ class, I'll call them p and q, and I never can remember which one goes which way. But anyway, the point is you can give them different names, and it's totally fine. Okay, so here I'm using x1 and x2, and you'll see why in a moment. But the idea is that we can define this thing called a point. A point is just exactly what it sounds like. It's a location in the plane. Right? But when you have these axes set up, you can assign to that point certain coordinates. Right? And then you can associate to those coordinates this ordered pair. Right? So given a point, we can, in this way, create an ordered list of real numbers that describes that point. So we have a geometric point of view on a point, and we have an algebraic point of view on a point. All right? Everybody happy? I hope this is very familiar to everybody, except for maybe that note. Oh, and hey, here's another thing. So this notation here, using the curly brackets. Y'all might not have seen that before. I don't know if you have. Curly brackets means here's a set. The line right here distinguishes where I'm showing you what these things look like from where I'm telling you the conditions that must be met to actually still be in the set. So you could read this as we're looking at the collection of all ordered pairs with the understanding, very important understanding, we're talking about ordered pairs of real numbers. That's one way you could read this. Okay. All right. You can do something pretty analogous in R3. In 3 dimensions. So you can talk about a location in 3-dimensional space, and for each location, you can correspondingly talk about these coordinates. Once you have those coordinates, you can correspondingly talk about this ordered triple. And so we view this ordered triple as representing that point in 3-dimensional space. Notation similar. Okay. All right, so R2 and R3. Now, here's where students get a little creeped out. But you can do something kind of like that in more than 3 dimensions. Right? Scary thought. So we call this Rn. Now, note algebraically, this is just a rip-off of what we've already written down. It's not really a new idea. Right? We're just looking, instead of ordered pairs of real numbers, ordered triples of real numbers, how about ordered intuples, we call them, of real numbers. Algebraically, totally similar idea. Don't try to visualize it. Sure, granted, right? But mathematically, you can still write it down. Now, a lot of people will ask at this time, so what's the purpose of this? We don't live in Rn. I don't know any 17-dimensional people. Why would I ever need to consider this abstract 17-dimensional world that I will never visit, ever? Right? So there's a great answer to that question, and that is that dimensions that we write down when we're doing math do not necessarily represent spatial dimensions. They just don't. If you take an econ class, intro econ class, it's very routine to have economic models that involve a bunch of variables that take different values, right, just like this, and except there might be 12 of them. I mean, economics is complicated. There's lots of things that involve lots of other things. I mean, capital and labor and interest rates and risk and, I don't know a lot of econ, but there's a bunch of stuff that's all involved, I feel sure, right? So you can easily write down, and I taught a class one time where one of the examples came up, it had 9 variables. You're technically doing math in R9, right? Don't draw the picture. Don't try to draw the picture. Your brain will melt, right? But you are still doing math in R9. Does that make sense to everybody? Okay. All right. So there's nothing, algebraically pointless about this. This is algebraically really, really important. And something's important to make sure everybody understands. Okay, but by the way, here's some other good news. The math of like how do you work out? We're going to start doing calculus of different kinds of functions. After we lay some groundwork. But the way you write down calculus in 2 dimensions, and the way you write down calculus in 3 dimensions, and the way you write down calculus in n dimensions, they're all pretty much the same, right? So when you write down these rules, you tend to understand them from the point of view of the pictures in 3 dimensions. But they apply, usually, there are some exceptions, but they usually apply in any dimension. Okay. All right. Okay, next topic, what's a vector? Now, a vector is a different concept. A vector in Rn is what we're going to talk about. And by the way, I'm going to say stuff like Rn, think R3, right, for sort of visualization purposes. And then, most of the time, same thing applies in n dimensions. So a vector in Rn is this particular pairing. It's this combination of concepts. It's a direction paired with a magnitude. Anybody seen Despicable Me?
Yeah, vector.
Yeah, there's the character, right? And when he introduces himself, he gives this whole little song and dance about... Anyway, you can look it up on YouTube. It's pretty funny. So I have a 4-year-old, so I've been seeing this movie a lot recently. So you might ask the question, well, why would we want to combine these 2 concepts? What do these concepts have to do with each other? And it turns out this particular pairing comes up a lot. If you want to talk about a displacement in physical space, I was here, now I'm here, right? Some sort of movement. Well, you moved in a direction, and by a certain distance, that distance is a magnitude. Okay. What if you're moving with a certain velocity? Well, velocity, if I'm going that way at 20 miles an hour, well, there's a direction and there's a corresponding magnitude. Now, in this case, the magnitude is speed, not distance. But nevertheless, this is a magnitude that helps me describe this physical quantity that I'm interested in. Right? So, various other examples. Forces, if you think about it. Direction and a magnitude. Right? Gravitational force. There's a direction. It's down. It's kind of the definition of down, right? So there's a direction, but there's also a magnitude. How much does this thing weigh? Okay. There are other examples. We'll talk about this one more next, but I want you to take just a quick moment and think about the flow of a fluid. An easy example is the air in this room. There's a little bit of a flow of air in this room, right? So, well, at any given particular point, I can talk about how the air is moving, and for example, you might say that at this point the air is moving in that direction, right? And then you could talk about how to make a magnitude. One way to do it is just talk about the velocity of the fluid at this point, right? There's your magnitude. There's different ways to do it. We'll talk about this point of view when we get into chapter 15. Let's not do that right now. Okay. So here is a vector in R2. Common mistake to think of this as being 3 vectors. This is not 3 vectors. This is a vector. These are all, you could say differently, the same vector. We represent vectors with arrows. You can guess why we represent vectors with arrows. Is because they're the easiest way to represent a direction and a magnitude. We let the length be the magnitude, and we point them in the given direction. So it's a very natural way to describe vectors. So, well, if you think about it, these 3 arrows, they have the same direction. I mean, forgive my imperfect drawing. But they're pointing in the same direction. They have the same magnitude, length, as I've drawn them. So they are representing the same vector. Everybody see what's going on there? A lot of students get confused on this point and think, well, no, vectors are arrows, and so that's one vector, and this is a different vector, because look, it's way over here. So, not so. These are different as arrows. These are different. They're not the same arrow. Arrows are drawn with a pencil. Right? The pencil lead over there is not the same as the pencil lead over here. So they are different as arrows, but they're the same as vectors. Okay. There is a natural correspondence between points and vectors. Now that's a little weird if you think about it. Points are locations. I don't see any directions in this story? What's the magnitude of that point? Points don't have magnitude. Points just they're infinitely small little things. They're just locations. It just doesn't seem. It does not look like a vector, right? But there is a perfect correspondence between vectors and points, and it goes like this: if you have a point, there is a unique arrow whose tail is at the origin and whose head is at that point. That arrow, this unique arrow that exists, given a point, there's that unique arrow. That arrow represents a vector. I can represent that same vector with a bunch of different arrows. All together, that direction, that magnitude is the associated vector. So you give me a point, there is an associated vector in this way. Everybody on board? Now, arbitrarily, I will confess, it is entirely arbitrary that we said let's start let's start this key arrow with its tail starting at the origin. Why did I pick the origin? That seems arbitrary. It is arbitrary, granted. This is a standard choice to make, though. You could, and in some situations not relevant to Math 212, one might reasonably make a different choice of a base point, not choose the origin. In Math 212, we always choose the origin. Okay, so you give me a point, there's an associated vector, and by the way, vice versa. If you give me a vector, right? If somebody says, hey, here's a vector represented by that arrow. What's the associated point? Well, that arrow has a direction and a magnitude. There is exactly one arrow with the same direction and magnitude as that one whose tail is at the origin. And that arrow has its head at the corresponding point. So it's the same correspondence, just backwards. Okay. All right. So here's the nice thing then, because these correspond in a natural way. If you want to describe a vector, you can do so by just describing the corresponding point. Right? We can talk about the vector whose associated point is the point, and then you write down the point. Or if you have a point and you want to describe it, as a vector, no problem. For that point, we're talking about the point that has the associated in this way the corresponding vector, and it makes perfect sense. So that being the case, we tend to kind of conflate the notations. All of these things are ways that you can describe either a point or a vector. It's arguably a little bit sloppy, but it's very convenient. So, for example, now this is, of course, something that you're going to think of as being a description of that point. Right? It's an ordered pair. Ordered pairs of numbers describe points. But, I can think of it as being a description of this vector. Let's try to draw well. This vector here as well. All right. Context will make it clear, by the way. So if you're moving along and somebody says the vector such and such has the feature that, okay, well, they said vector, right? So the vector x1 comma x2, okay, that speaker meant to say the vector that's associated in this way to the point x1 comma x2, but it gets real old saying that, and we know what we're talking about here. And so, like I said, context will always make it clear, and let's not obsess. Now, I will, that being said, point out that our book does obsess about this a little bit. Our book insists on using triangular brackets if they're talking about the vector, and they use the round brackets, parentheses, if they're talking about the point. And it's harmless, I suppose, if they want to, invest energy in this direction, okay. But I've yet to see a situation where the context doesn't make it clear as needed, and where this distinction of notation actually is necessary. Okay. All right. In Math 212. Now, by the way, if you ever take a course in differential geometry, the distinction is very important. Conveniently, in that context, there is no natural correspondence this doesn't make any sense. And so it's just really not a problem. I'm going to stop talking about that now. Okay. All right. Let's see here. Yeah. Okay. We've already talked about that. Okay. So given a vector, now keep in mind when you write a vector, we use length to describe the magnitude. I mean, that's just the convenient, when you draw an arrow, that arrow is a good way to represent vectors because, the magnitude for that vector needs to be represented by something, and the length of that arrow is a good geometric way to represent that magnitude. So, that being the case, magnitudes being lengths, that length being part of a right triangle, Pythagorean Theorem allows us to compute the magnitude of a vector from its coordinates. Real easy. Flashback to geometry. Hope everybody's seen that. Yeah.
When talking about magnitude, is there a difference between having two bars on either side or just one?
Yeah, no, it's a great question. So some books, and I can't remember what our textbook does. Oh God, they use one. Okay, so yeah, it's fine. I grew up mathematically using two bars. I like the two bars because just cosmetically, it's an additional reminder to the reader that, by the way, don't forget, this is a vector. But you're quite right. There's really no reason to do it. If you want to use a single bar, that's fine because there's no ambiguity. Now, I'll point out that there is this issue of, well, wait a second. What if we're talking about a one-dimensional vector? Right? If we have a one-dimensional vector, right, like this vector here, if I say single bar, couldn't that be interpreted as absolute value instead of magnitude? I guess it could, but here's the good news: they're the same, right? So yeah, sure, it is possible that this could be confused for something identical to it, and it's just not a problem. All right. So yeah, single bar is perfectly fine. Suit yourself. I don't really have a preference. I'm going to keep doing it this way. I don't know. I just kind of never made the switch. It doesn't take me that much time. And I think some students might find it easier because, again, there's that visual reminder of what we're talking about. Okay. Great question. Now, here's an extension of the above idea. Suppose you have a vector in 3 dimensions, and you want to talk about its magnitude. So we want to talk about this length. Well, that length is not the hypotenuse of somehow this triangle, because that's not a triangle, right? So how are we going to figure out what that length is? And the good news is this is an easy little geometry problem. I'm going to leave this as an exercise for you all to to fill in the blanks. And the hint I will give you is this. Right? And with that in mind, I want you all to check that this is the result. Okay, and that said, notice how algebraically similar that is to the one above. Cosmetically, it looks the same. I emphasize, this is not true because it looks like it ought to be true. It's true, full stop. Oh, and isn't it nice that it also looks like it ought to be true? Okay. All right. Okay, so let's talk about how to add vectors. And I start with the question, what should be the definition of V plus W? And I just want to talk about the sort of the underlying, the implied philosophy there, which is, let's talk about what definitions are. And ultimately, definitions are choices. There was a time when this notion did not exist. And then someone said, hey, I'm going to define the notion of adding 2 vectors. Well, what was the motivation of that person to write down the formula that they wrote down? And I think a motivation should have a justification. I mean, there should be some reason why you write down a definition. Don't just write it down because it's, algebraically it seems like, aren't I kind of supposed to do this? No, there should be a reason. So, just for example, when I was a little kid, I was frustrated at having to learn my multiplication tables. It's annoying. What do you mean 4 times 7 is 28? That's weird. I got an idea. How about let's just change the rules? Let's just make 4 times 7 equal to 47, and we could all just go home, right? So that seems awfully efficient and reasonable to me. And of course, this is silly, right? Now, let's talk why specifically this is silly. This is silly because there's no geometric interpretation of my little formula that I came up with. On the other hand, if that's 4 and 7, the standard notion of multiplication connects to geometry in the sense that area is 28. So multiplication, however annoying it is to have to learn your multiplication tables, that inconvenient choice of a definition means something to the geometric or physical world. Right? That's why you define things. There's got to be a connection to something meaningful. Okay, so let's go back to our question here. What should be the definition of V plus W? What do we want this notion to connect to in the physical or geometric world? And let's remember that each one of these vectors I can think of as a displacement, and I make the following modest suggestion that, well, if we have one displacement and then another displacement, I could think about what happens if I do them in succession. If I compose those displacements. So, if I displace myself as indicated by the vector v and then subsequently displace myself as indicated by the vector w. Altogether, I have displaced myself. The story began here, and by way of a process, I ended up being here. Altogether, that's my, what you might call, total displacement. Well, if displacements are represented by vectors, and if the combination of displacements looks like this picture, maybe this is what it should mean to add 2 vectors. Reasonable, I think, physical, connection to the physical in motivating a definition. So that's the definition I want to, correction, that's the motivation that I want to start with. Everybody on board with that? Everybody see how this is not an arbitrary choice? Okay, now, here's what I'm going to loosely call some bad news. The bad news is that the corresponding formula is really easy to write down. And I say bad news because this creates confusion. A lot of students look at this formula and think, oh, well, of course. Well, that's obvious. And I emphasize this is not obvious. This is a choice. I am choosing this formula because it gives me a picture that makes geometric sense. I am not choosing this formula because, I don't know, aren't you kind of, when you add things, isn't this just like, isn't that what you're supposed to do? Or something like that. Everybody see the point here? Right? So this, the direction goes, the implication goes that way. Because of the picture, that's why we have the formula. It is not because we arbitrarily and meaninglessly write down this formula like 6-year-old me that we get, that we are forced to accept this geometric consequence that is backwards. Okay. All right. So, similar story. What should it mean to multiply a vector times a scalar? Well, I think it's a reasonable thing to say that if you have a displacement, 3 times that displacement, do that displacement 3 times, right? It seems like a reasonable choice in the context of displacements. And this picture then, not hard to persuade yourself, gives rise to that formula. Okay. That's an easy sell. Okay, here's a theorem. I'll give away the game. I'm going to suggest that y'all prove this theorem. This theorem is extremely believable. A lot of students misunderstand where these absolute values come from. That's an absolute value of this scalar c. A lot of students think as follows. Well, suppose c were negative, this being a magnitude is by definition positive, and this being a magnitude is by definition positive. And so it just wouldn't do to have this be negative. And since it would be a problem if we just chose to put c in there, we're going to choose to put absolute value of c in there to avoid the contradiction. Okay, and this, again, very wrong. Now, why is that wrong? Well, because we don't get to choose theorems, right? So you've got to derive this result. And if you were to try to derive this result, you would have to commit a little bit of algebraic crime. It's because it's not true. This is not a true theorem here. Okay, this is the true theorem. Now, so where in the algebra does the absolute value come up? It comes from this right here. Common misconception. A lot of people are told in, I don't know when this is, 5th grade, something like that, that square roots undo squares. And so square root of k squared must be k. Well, that's just not true. Try it with any negative number. It doesn't work, right? Related confusion. A lot of people misunderstand what this symbol means. A lot of people think that symbol means the two different square roots of that number, or all of the square roots, however many there might happen to be. And that's not what this symbol means. This symbol means the positive square root. That symbol means positive. Okay, and so by the way, if you remember the quadratic equation, this whole story. Notice you got to explicitly write plus or minus. Because if you don't explicitly write plus or minus, that square root symbol just means just the positive one, and you've not found both of the roots. Okay. All right. So anyway, keep that in mind. Keep this in mind, and then you can prove this theorem. This is a nice exercise. I'm going to leave this as an exercise for you guys to do on your own. Just do it, by the way, for vectors in R3, just to avoid having to write ... But make sure you can do that with this discussion in mind. All the tools that you need to prove that result, we've just talked about. Okay. If you have any trouble with this, come to me in office hours. I'll be very happy to show you how it works and talk about it. And by the way, I also like to interject at this time that this kind of thing, I'm going to be doing a lot of this where I'm going to say, here, you finish that. Because again, as I mentioned last time, there's just not enough minutes, and I only get 50 minutes. And there's a lot of ideas to talk about, and the most effective way that we can use our time is not necessarily to do all of everything. Right? So some things I think the most effective choice is for you to do some things that I think you can or should be able to do, and then I'll go and talk about other things. Related to this, I will point out that when I leave an exercise for you to complete on your own, it's because in my mind it's sufficiently interesting that you should make sure I want to make sure you know how to do it, and it's something that you should be able to do, but that some of you might find a little bit challenging, and therefore it's worth actually making sure that you can go through and do it. And if you think about it, that's actually pretty similar to the thought process, the list of desirable characteristics of an exam question, right? Something that's relevant and that students should be able to do, but that some students might find challenging, so it's the same thing. So it is not even deliberate, but sometimes coincidentally, something that I have in class said, oh yeah, this is a good exercise, why don't y'all work that out, has shown up as an exam question. So that's another reason to do these. So when I say here, you do that, it just might be an exam question. And again, not that I will do it deliberately necessarily, but it might just kind of work out that way. So please do give a little bit of time to thinking about that. Okay, let's talk about subtraction. We don't get to choose how we want to subtract vectors because we've already decided on some choices that actually dictate our idea. So hope this comes as no surprise, but v minus w has to be the thing that I add to w to get v, right? I mean, if I want algebra to work at all, which I do, then I'm kind of painted into a corner. I really have to make this choice. This picture has to tell me this has to be my motivation for v minus w. So there's different ways you can think about this. Obviously, you can think about this as v plus the negative of w. By the way, if you think about it, a negative just turns the direction around backwards. Easy to motivate. So that's one way to think about it. Here's a different way to think about it. This is just sort of an alternative, but let's go back to how you add vectors. The process of adding w, you can think of as moving the head. Okay, what do I mean by that? Well, we started off with v, and then when I added, the head moved, as indicated by the vector w. So think of addition as displacing the head of the other vector, right? And along those same lines, you can think of subtraction as moving the tail. So there's the vector I started with. Subtracting w, I moved the tail to get that result. It's a different point of view. For myself, I honestly always think of subtraction. I have to go through this little addition game. I always think of, okay, this thing, well, it's the thing that when I add it to w, it gives me v. I don't know, I find that most satisfying for me personally. Okay, here's some algebraic facts about the operations we've just defined. Remember, we just defined vector addition a few minutes ago. We just defined scalar vector multiplication a few minutes ago, and that brings up questions that, do these algebraic properties hold? Now, I want to point out that just because we wrote down a bunch of stuff that cosmetically looks like this back in 6th grade doesn't mean that it will necessarily apply to these brand new operations that we just made up. Right? I mean, addition of vectors is not elementary school addition. It's motivated by this totally different concept. Maybe it was a little presumptuous of me to go ahead and use that symbol, right? It's not the same operation. So these properties down here, this is not a flashback to old stuff that you learned back in middle school. These are brand new facts because they are they're applying to brand new operations. So that brings up questions. Are these properties true? And again, they're not true just because they look familiar. And they're certainly not true because we shudder to imagine a world in which they're false. Right? Sometimes bad things happen, right? There are some operations we're going to write down where I'm going to have the sad duty to inform you that they do not behave the way that you really wish they would. So, anyway, here's the good news. These are true. Right? These are things that you can prove. It's a nice exercise, and you ask yourself, how would I go about proving this fact? And, we have formula for vector addition. You can break down a vector addition into coordinates. So write down in coordinates what the sum of v plus w is. Then write down in coordinates what the sum w plus v is. And then just confirm that, in fact, you get all the same coordinates, and therefore these are the same vector. Okay, so I think everyone would be well served to do, one of these. If you do one, if you're comfortable with one of these and how it works, the others are all kind of analogous. Okay. Here's a new idea. A vector of length 1 ends up being an important concept. It's a tool that we're going to be using a lot in Math 212. Roughly speaking, it's because sometimes we want to talk about just a direction. Now, if you think about it, a vector is a direction and a magnitude. Right? It's a direction and a magnitude. If I want to talk about just the direction, I would like to somehow talk about. Arrows have this nice feature of pointing in the direction that I'm trying to describe, but the magnitude is supplying more information that I don't really want to talk about. So the idea of let's just pick a vector whose magnitude is 1, the most boring number that we can think of, right? That somehow this we can think of as just as exclusively describing a direction. So it's a very common choice. We're going to do this a lot in Math 212. When a question asks you, find the direction that blah, 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 go ahead and assume that by direction, what they're asking for is a unit vector. Okay, so a couple of examples, not hard to persuade yourself that's a unit vector. The magnitude of that's 1. By the way, the notation that this book uses for that is I hat. The book. So here's 3 vectors that the book makes reference to a lot. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are surprisingly important vectors. The book refers to these as I, J, and K. And the little hat is code for a unit vector. But you don't colors. You don't have to do that, and I don't usually bother with that. If you just want to put the arrow over, it's totally fine. I would prefer to call these E1, E2, and E3. And you might look at this, the choice that I've made here, and say, okay, well, there's more ink, there's more pencil lead if you write it this way, so I'm going to go with the IJK, and that's fine. For Math 212's purposes, that is fine. I will point out for your future, applications of these ideas, though, that sometimes, if you're an econ major, or if you're an engineer, and maybe you're going to be studying some system that has more than 3 parameters involved, which, by the way, is going to happen, right? You're going to run out of letters. If you have 4, what do you IJKL? If you have 12, it gets weird, right? This green notation over here, no problem, right? So I kind of got over that whole IJK thing at some point, and I haven't looked back. I always do it like this. But anyway, suit yourself. Here's another unit vector. Not hard to persuade yourself. This is again, a little Pythagorean computation. So punch that up. Turns out this has magnitude 1. It's kind of interesting. Whoops. Okay. Neat trick. If you have a vector, if you have a non-zero vector, and you would like to find the direction that vector points in, namely, if you would like to find a unit vector that shares the same direction as the vector that you wrote down, here's a cool little formula that'll do it. Right? This formula totally does that. Just take the vector that you've been given, divide it by its own magnitude, and there's a unit vector. It's easy to prove that this is, in fact, a unit vector. I'm going to prove that that's a unit vector by computing its magnitude and showing that I get 1, because that's the definition of a unit vector. Right? Everybody see? So I'm just going to take the magnitude of this thing that I claim is a unit vector. By computing the magnitude and getting 1, I show that I'm right. And so we just have to do this calculation right here. That's a scalar that I pull out with absolute values. Don't forget the absolute values when you pull out a scalar. Good news. This is positive, so it is its own absolute value. Magnitudes are always positive. Even better news, those cancel, and indeed we get 1. Okay. By the way, I recognize this is a mishmash of little small topics. This is a bunch of little micro topics that we have to throw in before we can start doing sort of bigger things. So here's another one. New idea, something called a linear combination. This is a surprisingly important construction. This is what I like to call the fundamental construction of the field of linear algebra. By the way, how many people are engineers? I'm just curious. Okay, you will be taking a linear algebra course at some time while you're, if you stay an engineer, which I hope you all do. So linear algebra 216 is the one that most engineers take. By the way, I've been teaching that recently, so I'll see you there. But 221 is another good choice if you're thinking about a second major in math. 221 is the course that you should take. Again, if you're thinking about a second major in math, come talk to me. Stuff we should talk about. So, but anyway, in linear algebra, there's a lot of stuff that gets discussed, but it's all deep down, all fundamentally resting on interesting things related to this construction, the construction of a linear combination. So here's what it is. A linear combination is a sum of scalar multiples of the given list of vectors. Right? So altogether, anything that you can make as a sum of scalar multiples of a given list of vectors, that's called a linear combination of those vectors. Okay, so I just needed to explain that word. We're going to say this term linear combination a bunch in this class, even more in 216, but certainly some in this class. So that's what it is. Here's my first instance of that. Here's a true fact. Not hard to persuade yourself of this. Make sure you can multiply out why this is true. A little micro exercise. The interesting thing about this is this shows a weird feature of these vectors. Now let me remind you, these vectors, E1, E2, and E3, that we were talking about a minute ago. These vectors have this weird property that when you write a vector as a linear combination of those E vectors, according to this formula, the coordinates of the vector are the coefficients in the linear combination. That's kind of neat. So, in fact, this is the only list of vectors that has that feature, for which, in a linear combination, the coordinates of the result are the coefficients in the linear combination. And that's, not hard to prove. So that's a wonderful feature for this trio of vectors to have. Again, I remind you, that's these vectors right here. All right, so make sure you can see why that works. By the way, with that in mind, these are special vectors. These vectors have a name. We typically refer to them as standard basis vectors. So I'm going to be using that term a lot, standard basis vectors. So heads up. By the way, there's a reason why we call them standard basis vectors. I'll tell you that one in Math 216. Okay. All right. Okay, now on to something a little bit more interesting. Let's define the multiplication of two vectors. Right, now, here we are again. We want to define something. Definitions are choices, right? So we need to ask, what is the reasonable choice? We could make up some arbitrary formula and just write something down, But would it be meaningful, or would it be a 6-year-old me redefining multiplication? 4 times 7 is 47, sort of thing. It's real easy to come up with all sorts of garbage choices like that. Okay, but is there a definition that we can make of multiplying two vectors that actually connects to geometry? And it turns out that, in fact, not only can you do it, there's actually two good ways to do it. So that's the weird thing. Even though we will talk, with the word add or sum, right, we will talk about only one kind of addition of vectors. There are actually two really important multiplications. So you simply, with that in mind, you cannot talk about V times W. The semantics just doesn't mean anything. If you say V times W, I'm going to say, I don't know what you're talking about. All right, what do you mean? Which one? Which times? Right. Okay, so there are two of these that we're going to talk about. The first one now, we won't get to the other one today. That'll be tomorrow. But the first one's called the dot product. And the dot product of a pair of vectors is defined by this formula. It's a simple little formula. You take the coordinates of the first vector and the coordinates of the second vector, and you multiply and add in this way. It's called a dot product. And it's a weird looking little formula. Granted, yeah?
How does the dot product get rid of the
This is just a definition, right? And what I owe you, after having written this down, I owe you some sort of satisfaction that this is in some way geometrically meaningful, right? And you've kind of put your finger on the first sort of awkwardness of this definition, and that is the product of two vectors is not a vector. This dot product does not produce a vector. Now, it's a free country. I can define anything I want, right? I'm making this definition because I know how this story ends. I know this is going to have something cool is going to happen pretty soon. But I'd say right off the bat, it looks like a weird choice. I mean, what if someone were to come to you and say, "Yeah, I'm going to define the product of two real numbers to be a function"? You'd say that's why. You're going to have to. You got to give me more than that. What is it? Why is this natural? Okay. So here's the first pitch of why we like this thing called the dot product, defined by this formula. And look at these three algebraic properties that it satisfies. By the way, you can check all three of these properties, and I think you should do at least one. Be a good exercise. And again, the way you check that two things are equal is you compute both of them and then just confirm that, yep, same thing. Right? Easy to check, but nevertheless something you got to do. Okay, now, should you be impressed by this? And I'm going to say not very. So, certainly, let's go back to our philosophy. How do we make definition? What's our motivation when we make a definition? Is our goal here, if only we had a way to kind of sort of multiply vectors in a way that allowed me to do algebra? No. Right? Algebra is a tool. It's a tool to understand geometry or the physical world or something like that. So the fact that this is algebraically well behaved, that does not help me do anything. If there's no connection to geometry, then this will never help me, build a better bridge or something like that. I need a connection to the physical world. Okay. By the way, here's another reason you should be not impressed with this. Here, I'm gonna write down a different product. And by the way, this is totally non-standard. I'm making this up. So if you write this down, don't make sure. Here, let me just go ahead and do this. Okay, so this is silly. Okay. All right. Nevertheless, I'm going to define a kind of a multiplication. I'm going to use a triangle because that's weird, and they'll never see that again. I'm going to define a new kind of a product called V triangle W. And it's computed by the following formula. It's V1 times W1, and that's it. This triangle product that I just made up has all three of those properties. And absolutely no physical relevance. Okay, so don't be impressed by these blue properties that I have outlined. These are useful tools. We need them, but that alone is not why we care about the dot product. That's unimpressive. Okay. All right. Now, next pitch. There are some geometric properties. V dot V. If you take any vector and dot it with itself, you get the square of the magnitude of that vector. Now, this is easy to demonstrate. Easy little exercise. Make sure you can do that. Right? Nevertheless, there's our connection to geometry. Dot product on the left, geometry on the right. Magnitude is a geometric concept. It's a length. Okay. All right. That's kind of cool. Now let me begin kind of play devil's advocate here. This only works if you're dotting a vector with itself. How often does that come up? Right. Most of the time, you multiply something by something else. So this has got very limited impressiveness. Here's the first really neat one. This is called the Cauchy-Schwarz inequality. When you dot two vectors, the absolute value of that dot product is always related in this way. It's not equal, but it is less than or equal to a product of two lengths. Again, intrinsically geometric concepts. Right? So, this is any two vectors. This is starting to get this is an eyebrow raiser at this point, right? Now, on the downside, it's not equal, it's less than or equal, so there's a comparison happening. There's a certain amount of sloppiness, you might say, in this result. But nevertheless, it's really weird that this is true, and it ends up being really important that this is true. We're going to see more of this in Math 216. It turns out that there are some amazing results that follow from this. Furthermore, this motivates certain concepts that allow us to do amazing applications. So we're going to talk about a generalization of... I'm on a tangent. So anyway, but cool stuff to follow. Here's the one that Math 212 students like the most. That's this one right here. And this has got sort of everything you could possibly wish for. Any dot product equals, none of this sloppy less than or equal nonsense, right? Equals geometrically natural notion of magnitude, geometrically natural notion of magnitude, and then there's an angle, another geometrically natural thing. So the right side here is very geometrically natural. The left side is the full dot product in full generality. That's pretty neat. Yeah? Okay. So let me prove that. So this is a fact you should make sure to remember. By the way, it's a really surprising fact. Let me just remind you what the dot product is. The dot product comes from three-function arithmetic. Right? This is arithmetic that you knew how to do in the 5th grade. And yet it always equals this arithmetic, which involves square roots and trig. Right? I think that's super weird. If someone were to ask me, if I didn't already know this stuff, and someone said, hey, yeah, could this formula always equal to this formula? I would kind of laugh at them and say, don't be ridiculous. You can't compute trig with three-function arithmetic. Come on. Or if you did, it'd be an infinite series or something like that. It just doesn't look like it could possibly be true, but it is. Real weird. So here's proof. Very cool proof. Here's our picture. First vector, second vector, angle. Don't forget we know how to subtract vectors. There's v minus w. And I'm just going to write down 2 true facts about this this little scenario we've created. First, I'm going to look at this triangle, and I'm going to cite the law of cosines. I hope you all remember that there is this thing called the law of cosines. I feel fairly sure none of you actually remember the law of cosines, right? But there is this thing called the law of cosines, and I want to remind you that the law of cosines is it's a modification of the Pythagorean formula, that the hypotenuse squared is the sum of the squares of the 2 other edges. It looks a lot like the Pythagorean formula, just with a correction term based on the fact that because that's not a right angle, obviously if it's not a right angle, the Pythagorean formula wouldn't actually hold, but so this is how you correct the Pythagorean formula for non-right triangles. So anyway, I don't know if you ever saw that point of view on the Pythagorean theorem, on the law of cosines, but anyway, it's cool. So anyway, true fact. But here's another true fact. This thing that we just computed, well, we know magnitude squareds are a dot product of a vector with itself. I can FOIL this out. Right? First we have v dot v. That gives me magnitude squared, et cetera, et cetera. And so therefore this equaling this tells me that this is equal to this, and those cancel, and these cancel, and then I can cancel this common factor of -2, and I get what I wanted, that this is equal to that. Anybody see how that works? The neat result. Who knew that the law of cosines would be useful at some point? Certainly not me when I was taking geometry class. Okay. By the way, here's another exercise for y'all. use this result to derive the Cauchy-Schwarz inequality. Just take the absolute value of both sides and think about what that gives you. It's an easy little argument. Make sure you can write that down. By the way, I emphasize a common mistake students will make sometimes is to hey, wait a second. Oh my gosh, I went 5 minutes over time. I'm sorry. This is 10:20 to 11:10, right? Okay, sorry about that. I had in my mind I was going till 11:20. So, okay, we're done. I'll pick up here next time. I'll try to keep my eye on the clock again next time. Have a good one.